yeah, didn't expect this big audience, but yeah, thanks so much. So today I'll be talking about Plank, a new EVM smart contract language that I was working on. And yeah, Martin already gave an intro, but I'll quickly talk about myself and like how that relates to the project. So I'm Philip. I'm also known as Philogy online, and I've been developing smart contracts and auditing them for about more than 5 years now. And for the past 2 years, I started tinkering with compilers and things on the side. And at the end of last year, about 6 months ago, I started working on Plank full-time. And my motivation with this is that, over the years working so long with smart contracts, primarily Solidity and Ethereum, I started to become quite frustrated with the tools, but also more importantly, like how the tools were progressing. Like since I started to 5 years later now, it doesn't seem like that much has changed. Like we have Foundry now. So that side of the tooling is much nicer, but the language itself hasn't really changed. And that has caused me a lot of pain, both as an auditor and developer, and I want things to get better, and I just wasn't really seeing it, so I wanted things to get better. So that's why I started Plank, this new language. And specifically, the main pain point I want to zoom in on is that building larger, more sophisticated projects, I wanted abstractions for my code that scaled with my smart contracts, not against. I noticed that as I worked on bigger and more sophisticated things in Solidity, as you want to stack abstractions in a big code base, you want more data, be able to easily keep track of how things work. I noticed that the fundamental cost of Solidity in terms of functions, structs, all of that started adding up, and the bigger my projects grew, the more time I spent getting the low-level things to work well, because every layer of functions added gas, every struct added gas, and I couldn't just focus on the main logic, on the main security. I had to focus on gas all the time. And this left always like a lot of small security things on the table that they really add up. Like they cause you to miss things that go into audits later, that cause your development cycle to be longer, that cause your risk of being hacked to be larger, and all these like small things that really added up. And as an auditor, I also noticed like the really experienced devs like Zero Age from Seaport and other people, like because Solidity is this way, it really caused them to almost be afraid of writing like readable normal code, because once you get really deep into Solidity, you start to understand how much every little thing that you take for granted costs. And when you are aiming to deliver the best transaction costs, the best experience for your users, that really starts to matter, and that means that you just have less time in the development process left to focus on the actual application itself. And that's something I want to solve with Plank. I want the abstraction to scale as your project grows. So in this workshop, I'm going to give you a quick overview to introduce you to the language. And then I'm going to dive straight into project setup and a live walkthrough. So I structured it in a way that you can hopefully follow along and implement with me. And depending on how much time we have, we will implement quite a few parts of an ERC20 from scratch. So yeah, let's get straight into the language. So a quick overview. So Plank has 3 main pillars as a language. It has all the basics you would expect from a programming language. It has functions, structs, control flow, variables, all the basic stuff. Also imports and modules. And then the second piece is the smart contract piece. So the language is built on the bedrock of low-level EVM primitives. And the reason this is so important is because for you to be able to kind of let go of the low level as a developer and really trust that whatever you do is going to perform well, is going to have good gas costs, you need to know that you're building on a foundation that is well optimized, that is doing the things, doing the heavy lifting for you in the background, and that is only possible if someone is actually working on that, right? And to do that, you need to have the tools to access the lowest level, and sometimes when you're working on a more intricate project, you just need to access that level yourself. So this is why it's super important to me, but unlike Solidity, there is no inline assembly. So whether it's low-level code or high-level code, you can create functions, you can create abstractions over it, you can reuse low-level code, you can import functions. There's no like this artificial like inline assembly barrier that you need to cross every time you have data or variables that need to move between those 2 realms. And then lastly, in kind of like the superpower of Plank, and what makes me personally very excited, is comp time. So comp time is like this umbrella of features that enables a bunch of things that I and other developers have been asking for a while from smart contract languages, which is generic structs, functions, and zero-cost compile time evaluation. So this last one is pretty cool because essentially what it lets you do is you write normal Plank code, and you can tell the compiler run this during compilation only. So you can have some logic, you can have static checks, you can even have unit tests directly embedded in your code that run at compile time and they disappear. They cost nothing at runtime. It's run once and then free for your users. And then also, more importantly, it gives you macros, so you can do metaprogramming and code generation, but without any special syntax. It's mostly just normal Plank code, and this lets you really customize the language, and also as the language creator, this lets me more scalably and quickly iterate on the language because most of the features are implemented in the language itself. The core can be quite minimal. So I want to directly show you the syntax just so you can start downloading it into your brain and get some familiarity with it. So it's a mix of Rust and Zig inspired syntax. So you see here the syntax for importing stuff from the standard library, a comment, how you define a struct. We have here function, and the syntax for defining a function you'll see is a bit weird. It's a constant that is assigned a function. And the reason I do this actually is so that no matter how your functions or constants are defined, you can easily find them. And more importantly, your LLMs can also easily find them by just grepping, versus if there's like specific syntax for each. And then yeah, you have some basic control flow. You have an if, you have an option type, you have some parameters, you have the return type over here. And yeah, we don't have enums just yet like Rust or Zig, but luckily thanks to comp time and the generics, we're able to make something that looks similar. And this weird +% or -% is actually the unchecked version of the arithmetic operators. So that's also something I wanted to fix, is that it should be easy to read and recognize when something is unchecked, and more importantly, it should be easy to mix, because I noticed in Solidity you have like your unchecked blocks everywhere and variables defined outside, so you can transfer it, and I don't know, it gets messy, so little feature I stole from Zig to hopefully make smart contract development easier. Then I want to give you an example of doing low-level EVM things. So this is what low-level code looks like in Plank. So for example, here we have a function that from scratch implements emitting an event, and we might actually use this in a sec for ERC20, but you'll notice we get some memory here, and then we store something into memory, and then we directly access like the log3 opcode, which basically tells the EVM to emit something. And you notice here there's no inline assembly syntax that tells the compiler, oh, I'm switching from high level to low level. You can wrap this in a function, you can pass in parameters, and for example here this address type, which is actually a struct, you just access .raw, even though it's low level code, you can pass structs around between low level and high level code, which makes it very nice to encapsulate and reuse. And then lastly, we have an example of comp time code here. So this is kind of like a macro or generic function that computes the header encoding size for ABI. This is kind of like a low-level detail, but I wanted something that fits on the slide. But basically what this demonstrates is you have a generic function here that's defined as acting over types, and then based on the type you say, okay, the size is 32, and then if it's a struct, you have this procedure that basically iterates over all the fields and sums the head size. And right now this still looks a little bit rough because certain features are missing from comp time, so in order to do iteration, we need to do it via recursion. So it's uglier than it needs to be, but this is something that will be fixed very soon. But yeah, just so you have a taste of what that looks like. And then finally, a generic struct and function. So you see we have a generic struct is just a function that returns a type. Actually, you take the type as a parameter, and I think this can be much more natural than potentially in other languages where you have a special syntax for the generics and types, and this is kind of like a separate realm. In Plank, this is, at compile time, it's almost like a dynamic language, like you have the full power and ability to just look at types, generate code based on that, and then here you have a generic function. So lots of talking, let's get to building. I don't know how many of you want to actually do the workshop or like follow along, but if you don't, that's fine, I'll do it live in front. Thanks, Martin.
No problem.
Let me grab a quick sip. All right. So here's the link and QR code. So this is how you install Plank. It's a one-line installer, similar to a lot of other tools. This QR code will hold all the links that you need throughout the workshop, from the installation instructions to also like various extensions for your editors. So this process will actually automatically prompt you to install the VS Code extension. Also for security reasons, because people historically have gotten phished through the marketplace, so the tool just installs it directly. And then if you have NeoVim, we also have a NeoVim extension for syntax highlighting. I personally use an EVM, so yeah, that was important to me, obviously. And then, yeah, let's write an ERC20. Don't worry if you didn't get the links. This is the same QR code and gives you all the links. So this is the GitHub template for the workshop. If any of you want the QR code one, we'll be going around with it to show you if you didn't see it. But yeah, looks like today people just mainly want to watch instead of follow along, which is totally fine. So yeah, let me dive into actually writing some Plank. So let me clone the template here. And this is Foundry based because we don't have our own testing framework yet. So we have a yeah, thanks. Thanks for the prompt. Okay. Big enough? Okay. So we have the template. This is just a Foundry project. So here we have already some tests. So we can see as we go along, we have some basic ERC20 tests so that we see that things are working as we enable features. And then also we have already a Plank file with all the constants we'll need. Because again, Plank is still kind of new, so it doesn't have some of the built-ins in terms of automatically generating the event signatures and hashes for you. This is also something that's coming very soon. But yeah, this file just contains all of them pre-computed. So let's go directly into writing our ERC20. So we will create a new file in our project. And already actually let's run the test just so it installs the Foundry dependencies. So it'll install the Foundry standard library and the Plank deployer. So while that's running in the background, we can write our first Plank file. So the idea behind Plank is that it should be very extensible, and for the experienced devs, it should give you all the raw power of the EVM, and then the standard library and tools around stack abstractions on top of that, so that when you really need, you can go to the lowest level, which means that right now in Plank, when you define a contract, you really have the raw init code or constructor code entry point, and then you have a run entry point. And the run entry point is actually even optional in case you want to have like fully custom bytecode given from your constructor or other advanced use cases. But in our case, we want to have a runtime, so we'll import from the standard library, from the constructor, our return runtime function, which basically all this does is it looks at the runtime code and returns it, and this basically just initializes your runtime because at the lowest level of the EVM, there's your init code, and all the EVM cares about is what that init code returns, like the bytes that it returns, becomes your actual contract on chain. So basically, this does that. And then in run, we actually need to tell Plank how we want this function to end. So for now, we'll just say stop, like it'll just stop execution. And then now we'll see that if we rerun the tests, that they all fail because we haven't implemented anything yet. So that's the first step. So let's implement something easy first. Like let's take the total supply function. So in our token, we'll have a constant total supply of 1 million. So let's just define a constant of the initial total supply. And we'll set this to 1 million. So you can use underscores for your constants here in Plank. And then basically, because this is the raw entry point, it doesn't yet know about public functions or selectors and all of that. So this, again, allows some great customization and optimization in custom use cases, but this also means that right now we kind of have to code certain things from scratch. And again, something we're working on, and the boilerplate will be reduced in the future. But yeah, I think also, in general, I want to say that even if you never use Plank, I hope that at least with this workshop, you'll have a better appreciation or understanding for the lower level things that Solidity does for you under the hood. And when you do optimization or when you do audits, you'll have a better understanding of what's going on. So yeah, we'll compute the selector from scratch. So the EVM only lets us load call data in 32-byte chunks. So we read from the 0th byte because in the EVM, all it understands is, okay, your contract receives a call with some data, and then based on the data, it does something. But if you want multiple functions, the way we've standardized this in Solidity and other languages is that the first 4 bytes tell you which function to call. And so to be compliant with the ERC20 standard, we want to follow the same pattern. So we read the first 32 bytes using call data load, and then we shift it down to have just the selector, just the first 4 bytes instead of the 32. And then we have this magic number 224. But what does this mean exactly? It's because there's 256 bits, but we're actually keeping 32, which is 4 bytes. So to make this a bit readable, we can actually just calculate this out explicitly. And the nice thing about Plank is that anytime you have like some kind of arithmetic or computation, it gets embedded directly into the bytecode. So now we have our selector. And now let's actually look at our constants. Let's import them all from our project. So we have constants. We import them all. And then we match on the selector. So if it's the total supply selector, then we actually want to return the total supply. And because it's constant, we can just return the constant. So let's get the ABI encode function as well. So we have ABI encode. And the cool thing is a lot of the few things that the standard library already has are all implemented in Plank. So this should also help the language moving forward to develop very quickly. And we already have 2 external contributors who started working on the standard library since the launch. Because this means that to extend the language or to build on it, you don't need to be a compiler developer. You just need to know the language itself and use the same tools to extend it. So we want our actual our data. So let's define a struct for that. So our return data from the total supply function or others is just a uint. So let's do uint. Let's call this uint return data, and then we'll just have a simple struct that holds a single value. And the nice thing about Plank is that unlike Solidity, structs are not by default allocated to memory. So structs are essentially free in that sense. They just get converted to simple stack values, and it's the same as using variables. Like if a function accepts a struct with 2 fields, it's at the lower levels, what it gets converted to is the exact same as a function that accepts 2 parameters, versus in Solidity, it gets allocated, there's a pointer you pass around, you always have to dereference and access that pointer. So this just lets you more freely define types and use these abstractions without worrying about, okay, you know, it gives me a bit of type safety, but do I really want to add a struct here? In Plank, there's no such worries. So yeah, let's encode this. So encoded, our return data is the uint return data, and then we actually initialize the struct. Let me hide this for a second. And then we say that the value is just the initial total supply. And then we just do a raw return. So we take the encoded data, and then we take the pointer and the length. Because this is actually a membytes type. And yeah, this type inference, so you can, if you want, you can add type annotations here. Like you could add this, or you can leave it out, because there's a type inference, so it's optional here. And then we'll see that our first tests are now passing. And voila, we have our first function implemented from scratch in Plank. And then yeah, let's keep going. Let's implement balances. So to simplify the scheme here, we'll say that the address of the person is directly the storage slot, but you can obviously do a hashing-based storage scheme if you want. So let's do EVM store to the caller. So we'll just say the deployer gets the initial total supply. And then now we actually want the balance of. So let's take the balance of selector to implement the balance of function. And then if it's balance of, we want to actually first load the balance. So for this, we need a parameter, and we say, okay, the owner is the first parameter, which we read from call data at byte offset 4. And then we read their balance by doing the same thing in reverse. So here we just use the raw storage access that Plank provides us to read that based on the owner. And then we encode, we can copy this, we encode and return that. So let's take the value is the balance. And then actually, why don't we put this in a reusable function, because this is kind of annoying to type out. So return U256. Oh, small typo. And then we just say value is a U256. And actually, we can use the never type, which tells the compiler that actually this function is guaranteed to always end, and therefore we can actually use it at the end of the run or init block if we want. So let's wrap this in here, and let's say value is value. And you might notice a lot of things are a bit manual still. But really, if you follow along in the next 1-2 months, this will get much easier. But yeah, we literally launched our first version like 1 week ago. So this is just the very beginning for now. But yeah, let's do return U256, balance, and then we can also simplify it up here for the initial total supply to make it simpler. And now we should have more tests passing. So yeah, now we have 3 instead of 13. Now balance of works, and deployer has the initial supply. So let's do something a bit more interesting, actually. Let's do the transfer function. So let's get the transfer selector, and same process. All right, so we check if the selector is transfer. And one small detail here. So what's interesting about doing everything by hand like this is that when you do want to optimize, for example, the selector order, because this is the actual code that Solidity would emit as well, right? It checks the selector one by one by one. If you have a specific function that gets run very often that you want to have cost lower gas, you can just move it up. Versus in Solidity, there's no easy way to do this. You can use the fallback and you can manually in inline assembly do the same thing. But it's less ergonomic. And like if you look at, for example, OpenSea is a famous case of this. Zero Age wanted the order execute function, which was the hot path, to be more efficient. So he had to use a custom tool to mine a special selector for the order function just so that it would have 0 bytes and then Solidity would magically place it at the top. But instead of doing this, you can just customize that directly in Plank and do it like that. So let's get the balance of the sender of the transaction, which is just we'll load the balance of the caller. And then we want to check whether the balance is large enough. So one easy way to do this is just to subtract the balance because Plank supports the underflowing subtraction out of the box. So we can just say, okay, the new balance of the caller is their previous balance minus the amount. And we need to manually decode the amount, which is the second parameter. And let's put a comment here just to make it clear what we're actually decoding. So we have 2, which is an address, and then the amount, which is a U256. So we have call data load. And then this will be at byte offset 36. So that's the amount. And then we have updated the balance. And then the recipient is stored byte offset 4, just like in the other one. And this manual call data decode right now it's annoying, but I think it's also a cool thing that you can just, something so fundamental, like if this were missing from Solidity, there's no way you can add it yourself. But in Plank, this is just like a few dozen lines of comp time code, and you have your own custom encoder and decoder that works for any type, and you can add any optimizations that you want. So yeah, let's keep going. So now we've decremented the balance of the caller, and now let's hand the balance to the recipient. So we can actually showcase some shadowing of the variable here by loading now the balance of the recipient. And then we store. So technically this is not secure because we should sanitize the call data, etc. But we're gonna skip that for now. But yeah, balance, and then we add the amount. And then since we know the total supply is limited, we could actually even optimize here and say, okay, we don't have to do a checked addition. I would just add a little %. But I don't think that's necessary right now. And then we need to return true. So we want to be compliant with the standard. The ERC20 standard wants us to return true on successful transfers. So unless this subtraction reverts because you don't have enough balance, we want to return true, which is basically always. So what we can do is we can either know that a Boolean true becomes 1, and we just use return U2561, but this is not exactly type safe, right? This is a bit ugly, right? Like, why are we returning with a U256? So let's actually make our return function generic. Let's say return value, and then we'll say it works with any type, and this type has to be comp time known because, yeah, you only get like type dynamism at compile time because the entire language is statically checked. And then we'll say the values of type T. So we'll say the uint value. The uint value is if the type is U256, then the uint value is just the value, right? Because we know it's a U256. Otherwise, if it's a Boolean, then make a reusable conversion here. So based on the value, we say 1. and then you just do uint value in here. So now, this works both with U256, and here we want actually the Boolean, true, and it works with U256 as well. So let's put it here. So that would be your first generic function. And U256 here as well. All right, how much time do we have? We still have so quite a bit of time. Okay, nice, nice, nice. All right, so now if we run this, more of our tests are passing now. We have the transfer to self is working. We fail on insufficient balance. But certain things are still not working, like the transfer and transfer event, because we're not emitting a transfer event on transfer. So let's rewrite that function from the slide earlier, and let's do emit transfer is a function that takes in the from, the to, and the amount. So it's a bit janky that we're using the U256 type as addresses as well, so let's fix that real quick. There's a PR actually about to land to add this to the standard library, but it's missing just yet, so let's actually define the address type by hand. Who is an address? And actually, let's define a little helper that just directly gives us an address from message sender. So we'll say returns address, and it's just address raw EVM caller. So we have a little abstraction for that. And then we can actually also add it to our function here, so that we don't even need to change that. So if it's an address, we just say value.raw. And we've successfully extended our one function. So now we can actually change that here as well. We can say, I mean, here maybe it's cleaner to do it like this, to be honest. So let's keep that there. So let's handle the emit transfer function. So again, we want to encode. So the way under the hood that events work in Solidity and the EVM is that there's different log opcodes based on how many indexed fields you have. And the first one is the transfer, or your event signature, and the next are the index fields, and then there's a generic data field where you put all the non-indexed data. So for the transfer event, the only non-indexed data is the amount. So let's encode that here. So encoded, we have just the amount, and then what we do is, all we need to do is we do EVM log3, and then we have the encoded pointer, encoded length, and then we need our index topics. So the first index value is the from address, and then the to, and then we need to access like the raw U256 representation of the address, because all the opcodes mainly deal with U256s. And then let's get the transfer topic, and this is what tells like Etherscan, etc., that this is actually a transfer. And now we just add this here. So we have emit transfer from the message sender to the recipient, and actually we need to remember how I mentioned that we actually need to sanitize the address. Why don't we directly add that? So we can say to address, and we can create a reusable function that says raw and gives us address. And then if the raw is larger or equal to the biggest address, or the first value that is an invalid address, then we just revert. So we do a manual revert here. And then, so that's another detail of Plank, is that memory management is a bit more abstracted than in Solidity, where you have direct access to the free pointer. And the reason for this is because we never want stack too deep. And to be able to guarantee that, the compiler needs a bit of leeway in the memory layout. So that's one reason. And also in the future, we want to have, we want to be able to easily optimize memory use automatically for you. So if you have an unused allocation, or you're allocating something in ABI code, it should automatically compile down to the same code as if you manually like interacted with scratch space. That's why also, for example, there is no scratch space in Plank. You just always use the same primitives, and you just let the compiler take care of the memory for you. So this means that the comp time generated ABI code would be exactly as efficient as like a manually handwritten, like baked in ABI code. So yeah, once we validated the address, we can actually It's converted. Right now, there's no further protections that we don't accidentally, illegally initialize an address. But in the future, we plan to have public and private fields similar to Rust or other languages. But yeah, we have our address helper here. So let's wrap that here, and it'll actually now revert in the future if we ever try to pass an invalid value in call data. And then we have to load it here, but otherwise, access the raw version. But yeah, so then we made the transfer from message sender to with amount, and then let's see if that works. And voila, it passes. And all this time I showed you like basically every time what I type in works. So let's also look at what it looks like when the compiler actually fails. So for example here, it's type inferred, but let's say we accidentally mix up types. And then we build our ERC20, and then we want to say that it's a module named ERC20 and that the root is source. So we'll get a type error. So this is roughly what the errors look like. I try to spend some time to make the errors look nice and also be helpful. But yeah, if you have any issues, feel free to raise an issue on the GitHub. Always happy to fix that because yeah, good error message is also something that's very important to me because you know, copying the philosophy from other languages like Zig or Rust, I'm a big believer that an error at compile time is better than an error in testing, is better than an error in production. And Plank wants to help you as much as possible to move as many errors you can early in the process, because even if they're hypothetically simple things that an auditor would catch, these are potentially days or weeks and thousands of dollars lost in your development process. So anything small, even that you can catch early on, I think is very valuable. And leveraging the type system to help you do that is, I think, one way that you can do that. So let's go back to running the tests. All right, so now, what do we implement next? Let's do approvals. Let's implement approvals. So in the EVM, storage is just like a raw 32-byte key to 32-byte value store. So for approvals, where you have the owner and the spender, which is more than 32 bytes, how does Solidity or how do we turn that into a 32-byte key? So the way we do this securely is we do this via hashing. So let's implement that. Let's say, let's do get approval slot, and we'll say owner, spender, and then we'll get the slot, and then we just allocate some memory. So let me copy the malloc. So let's get a little buffer. We can do it by hand here just to demonstrate some manual memory management. So we'll get 64 bytes, so we can fit both values. And then we'll write into it, so buff will be a pointer. So I can have a manual type annotation here so you see what it looks like. So this is like a raw, just like a byte pointer that you can access when you need to write low-level code. And then we put the owner address there, and then right after, shifted by 32 bytes, we put the spender. And here I'm using addition. So this is generally the convention in Plank. So you have the normal operator like plus, minus, multiply. And then when you want to tell Plank that this one should not be overflow checked, like I know what I'm doing, or in the case of pointers, it's always, it only supports unchecked, you add the percent. So percent always, it's like modulo, it's like means wrapping, right? So it means that things will wrap. So we write the spender, and then we have our unique slot. So now that we have this, so we're saying we're hashing from the initial pointer 64 bytes. So now that we have a function to get the slot, and let me actually see that that compiles with our build command. Okay, it compiles. Let me put some optimization to make it a bit smaller. Okay, so we have our function here. Let's actually implement approvals. So we have, where's the selector? We have the allowance selector. So let's implement the get allowance function. So again, this is, we probably want to put this lower because it's going to be used less often than balance of or transfer. But yeah, we have here, we fetch the allowance. So first we want to decode the parameters. So we have the, let's just copy from here. So we have the owner, and then we have the spender, and then we have the slot, which is get approval slot. and then owner spender. And the nice thing is, again, this uses the address type, so if we accidentally mess up and try to pass in like a uint, like let's say raw, to get the uint version, the compiler will yell at us and say, hey, oh, we're using the, it also tells us about this error, we're using the wrong field, raw and raw. But yeah, it'll tell us like, hey, we want address, we got U256. So this comes down to a pattern that I really like in programming in general, in any language, called type-driven development, where you wrap common types in your own custom one-off types to basically get the compiler, to tell the compiler that this is a more specific version of that type. So this is not any raw U256, this is an address, or this is not any raw U256, this is a share count, or this is a amount of ETH. And this lets you write functions in a way where if you accidentally mess up and use one value where you're not supposed to, you use maybe a share count in place of like an ETH balance, like the compiler will yell at you and give you feedback very early in your development process that there could be a serious bug there. So we have the slot, and then we just read the allowance from there by doing sload. We read the slot, and then we can use the return value. Let me just paste that here. And then we should have more tests passing. So now we have allowance. Do we have any of the allowance tests passing yet? Not yet, okay. What does the allowance test actually do? It checks the allowance at the beginning, and then it checks that you can set the allowance, which we don't support just yet. And actually, at the end, if we don't match with any function, right? If somebody calls your contract and none of the functions match, to give proper feedback, you probably just want to revert. So let's just put a revert down here. And all right, so let's do the approve now. The approve. And then we'll say if selector is approve. And let's move this up actually, because this is probably going to be used more commonly. We'll get the spender at the 4th byte, convert it to an address, and then we can just say the slot is, so I'm approving the spender, and then we also want the amount. So the amount is here, and then we just store. So this has some like long known issues based on the ERC20 standard where you were overwriting your allowance. Definitely, so auditors might annoy you because of that. Well, I don't think people are seriously bringing that up anymore, but yeah, who knows. And then we can return true. And then that should be working as well. All right, now we have many more tests passing. So we have the approve test is still not, I think there might be an event missing. Right, we also need to emit an event here. Whoops. So let's do that. Let's copy this and make a approve event. Let's call this owner, spender, and it's pretty much the same. It's just approve topic, I think. Approval topic. Approval topic. And then we'll say owner, spender, and then let's emit that here. So message sender, spender amount. All right, two tests left, and we almost have a full ERC20. All right, now for the final big boy, we have the transfer from function. So transfer from function not only transfers, but it checks approvals, decrements approvals, does the whole 9 yards. So let's get that in here as well. Transfer from selector. So first let's see that that actually compiles. Okay, that's the correct constant. So now we want, also here's a comment, let's say from to. So we have from at offset 4, to at offset 36. Okay, and we have amount, and to make this a bit more readable, let's do 4 plus 32, and then 4 plus 32 plus 32. So we have from to. So first we want to check the approval. We want to make sure we have enough approval from the from person. So let's let's copy the get slot here. And we want to flip this actually because now we're the spender. So from message sender, so did this guy allow me to get the, to spend money on his behalf? So the allowance at the beginning, allowance, is whatever is stored at the slot. And then what we want to do is we want to see, okay, if slot is the maximum UN, so we can actually also do this as just not 0. There's many different ways that you can define the max UN. Actually, just so it's not a magic constant, let's do const max 256, and then it's, and then we just do, that's another way to define it. So yeah, so if this is a common optimization, if it's the maximum, if the approval is already the maximum, which is like a really insanely large value, it's essentially infinite, so we can save gas by just not updating the allowance at all. Or, right, so if we do this, we skip the thing completely. So I actually want to say if it's not equal to the maximum, and the allowance is less than the amount, then we want to revert. And we're reverting quite often in different ways, so let's actually put that in a reusable function. Let's call this empty revert. Actually, this might be in the standard library, I can't remember. Never, because it always reverts. So that's the return type, it never returns, because it never gets to the end. So let's put that here. Or let's just call it revert, actually. I don't think revert is a occupied name, so let's call it this revert. And then we can put the revert here as well. So, and then if slot is not equal to, or we can actually put this in here. So we have curly braces here, here, here. And then, again, if you have questions, just shout them out. I'm going a bit fast here because I think we're running low on time, or how much time do we have?
Anyone have any questions?
No? Okay. Then I'll just keep going. Then we want to update the allowance here at the slot. We do allowance minus amount. But we already checked it, so actually we can just do %. And minus %. And actually the minus already does the less than check. So actually I think the safest version is just literally storing here the updated allowance. And if it's too small, it'll just revert because of the checked arithmetic. So now that we have that, we can actually do the normal transfer. So we have the balance of the from, which is just from raw, and then we update from raw, and then otherwise the balance of the recipient to raw, and then we just do from to. And we're missing a semicolon. Actually, let me run the compiler directly to get the error more nicely. Okay, we're missing a semicolon right here. Awesome. And now it compiles, so let's see the tests. And voila, we have all the tests. So let me quickly just finish off the presentation. So yeah, hopefully that gave you a taste for what Plank can do. Admittedly, it's a bit raw right now, but yeah, stick around and it's going to get much better very quickly. And yeah, so what's the future? So we obviously want to make things less annoying by adding more primitives that other languages have out of the box, be more batteries included. Compiler optimizations, because right now we mainly are getting the language to work, but the bytecode size and gas are still not quite there. And we want to start with our hardening and formal verification efforts to kind of pave the way to make this actually usable in production. And then yeah, later in the year, we're going to have some very nice tooling like formatters and LSPs, and a more comprehensive standard library. And then yeah, next year will mainly be about really getting the compiler production ready. So yeah, didn't seem, oh yeah, question?
Is there a way to extend the language with the new opcodes for custom EVMs?
With new opcodes, not yet, but that's definitely something I'm thinking about adding, because that was also a problem I've seen with other languages, is that, yeah, rollups tend to add precompiles instead of opcodes, or also EVM. The Ethereum team itself seems to prefer to add features through precompiles rather than opcodes. So this is something I want to add. The only tricky thing in general about this with compilers is that the compiler likes to do optimizations by making assumptions over instructions. So if you define your own opcodes, you either need to expose an entire system to let users define, okay, does this opcode touch storage, does it touch memory, etc., or you just conservatively disable optimizations whenever you use the opcode. So I'm not sure, I still have to think about whether there's a nice way to expose this to users, but yeah, definitely something I'm thinking of, but no concrete plans yet.
And the last one, any support for arrays, or that's going to come from standard library?
It's going to come from standard library. So in terms of syntax, definitely going to add array syntax. You can already implement your own arrays using pointers and functions today, fully supported. I mean, fully supported in the sense that you could build it yourself, and that we will add it to the standard library soon. But yeah, in terms of actual like array-looking things, like you can use square brackets and all of that, not there yet, but also coming.
Thank you.
Thanks for the question.
Anybody else with a question?
Cool language, by the way. Yeah.
Thanks.
But if you can make one great feature right now, like without any kind of sort of work, but that can have great impact, what it would be, like some syntactic sugar or some feature.
In Plank, or you mean Solidity?
In Plank, yeah.
In Plank, I think the one big feature is strings. So there's no easy way to do strings right now. And the reason we had to do all this business with you know, the pre-hard-coded file with all the constants is because there's no easy way in comp time right now to write down a string and tell the compiler, hey, can you hash this and just do the derivation logic for me? And this one feature would enable all of that and more. There's other things that other languages like Solidity and Viper haven't added for years that I've wanted, like automatic EIP 712 generation, you know, like all the type hashing and all of that was very error prone. And just with strings, you could do all that. So that's like the next to-do item on our list, to just add strings, because you'll be able to manipulate them at comp time. You'll be able to do other things like, I don't know, generating lookup tables yourself at comp time for free, and then just embedding that in your bytecode and directly referencing it. Like so many cool things you can do just with strings. So yeah, that would be the one big feature, strings.
Cool, thank you.
All right.
Anyone with a final question? If not, then please let's all clap Philip for a very impressive presentation of Plank.